So I want to talk about polynomials. Now, this first expression of polynomials, this a to the n, x to the n, plus a to the n minus 1, x to the n minus 1, that looks a lot more complicated than it really is, than what it really means. Basically, all the a's, a sub n sub 1, or n minus 1, a sub n minus 2, and all, are just coefficients. And of course, in a polynomial, they can be 0. X is your variable, and then n, in the kind of polynomials that we're going to deal with polynomials that have integer exponents, and so we simply start, something like x squared plus 2x plus 1. All right, so let me give you a little bit more maybe concrete example of a polynomial. Here we have 3x to the fifth plus 2x to the fourth plus 3x squared minus 4x plus 1. Now notice we're missing one of the degrees in there. We're missing an x to x cubed. So that just suggests that the coefficient to that is 0. And so whenever you have a zero term, we can just leave it out and write it in its most compact form. So a few things to note, that the highest exponent is the polynomial degree. Okay, so in this case, this polynomial is a 5th degree polynomial. Now we have terms that are of the 5th, 4th, 2nd, and 1st degree, and a constant term, but it's when we call the polynomial by its degree, you look for the highest number. So it doesn't matter if you have other degrees in there or not that are lower. This is always a 5th degree polynomial because we have an x to the 5th and nothing higher than x to the 5th. Okay? All right, then the leading coefficient is going to be useful to us in a variety of ways. And so we call the coefficient in front of the term with the highest degree as the leading coefficient. Now if we just had an x to the fifth, our leading coefficient would be 1. Okay, now oftentimes our leading coefficient is positive, but it doesn't have to be positive. Leading coefficients can be negative as well. And then the last term that doesn't have any instance of x in there, we call that the constant term. Now, if you really want to write this kind of by the first definition, we have ax is the second to the last term. If we say ax to the 0th power, that's the same thing as just saying a, right? And so, in a sense, we can look at this thing as being 1 times x to the 0 power. The only problem that presents us is that 0 to the 0 is not defined. And so if we actually state the polynomial like that, we're saying that x is not part of the domain of the, or that 0 is not part of the domain of the polynomial. We do very definitely want x equals 0 to be part of the domain usually, so we concede that x to the 0 power just goes away as 1, and we just use that as a constant. Okay, so in standard form, we put this in order of decreasing powers. So what I just showed you was something in standard form, where we would have something like x squared plus x plus 1, decreasing powers like that. Now, if you get into calculus somewhere down the road, you'll get into sequences and series, and there they'll put the order of the polynomial in reverse order: 1 plus x squared plus x cubed, and there's a particular reason for doing that. But we're not going to go there. We're not going to do sequences and series, so we're just going to look at polynomials. And since when x is very large, the leading term in this last case was x to the fifth, that thing dominates the value of the polynomial. You always put that one first. So we have some specific polynomials. A monomial comes from mono, which is 1, and nomial just means it's derived from the same word that we use for name. So it has one name, one term, essentially is what monomial means. And then we have binomials. and two terms, and oftentimes binomials tend to be linear polynomials, like x plus 1 or 2x minus 3. You know, we've dealt with a lot of linear equations that you can call a binomial term. And then, of course, we have trinomials, three terms, and we'll spend a lot of time with those. That's things involving x squared plus 2x plus 1, polynomials like that. Now, I suppose you can keep on naming them, you know, with different names higher than that, but traditionally you just don't use it. Trinomial, binomial, and monomial we use. Anything else we just call a polynomial of degree 4, for instance, something like that. Okay, so if we write this thing in standard form, identifying the degree, leading coefficient, and constant, if we have something like 12 plus 4y minus y squared, in standard form, that would be minus y squared plus 4y plus 12. The degree is 2, the leading coefficient is negative 1, and the constant term is 12. Okay, so just a kind of an agreement of terms on how we're going to refer to these things. Now, if we have terms, I think we talked about this maybe the first week of class, that if you have terms that have the same degree and the same variable, you can just add the coefficients to combine them. So if we have something like 3x to the fourth plus 12x to the fourth, that makes 15x to the fourth. Or if we have 5x squared minus x squared, that's going to be 5 minus 1, which is 4, so we have 4x squared. Now, polynomials add and subtract exactly the same way, except that you need to pair up the terms that are like terms. And when we say like terms, we're saying that it has the same variable, the same exponent. Okay, so we're going to try and combine like terms, and really the only tricky part of this is keeping track of your positive and negative signs. So if we have a polynomial, x squared plus 2x plus 1, and we're going to add that to 3x squared minus 4, that simply then is the x squared plus 3x squared will make 4x squared. The 2x is the only instance of the first degree polynomial, so we keep that as 2x. And then we have, 1 minus 4, I made a mistake here, that's going to be 3. Like so. So you watch your signs, and so when we subtract, probably the best strategy to do this is in two steps. The first one is just distribute that negative sign, and then combine the terms based on what they look like. So in this case, we'll just remove the parentheses and apply the negative sign, and you can see that 3x cubed gets to be negative, the positive x squared becomes negative, negative 3x becomes positive, the positive 1 becomes negative. I guarantee you, if you're going to make a mistake on this, it's going to be this last term here. That, you know, you get, I don't know, something about it. Most people can do this reliably, negative 3, and you're going to add that to the 2x. But then, for some reason, the 1 creeps in there as just a positive 1 rather than the negative 1. So I really strongly suggest you just write it out, and then we can combine like terms, and we get our answer. All right, everybody follow? Okay, so go ahead and try these. I want to simplify these. Now notice on a couple of these, on 3 of them actually, I use some other variable than x. And of course polynomials work for any variable. That's just an arbitrary thing we choose. It's a very easy thing, and you've probably seen me do it, where when you copy something over, instead of using a t, you all of a sudden convert it to x. And most of the time that's not too bad, but try and pay attention to the variable and see if you can retain the variable with its original name, unless of course you have a reason to change it. Okay, so addition and subtraction I think are fairly straightforward. It's a matter of being very careful with the signs on it to make sure you don't make a sign mistake on those. And don't be afraid to write things out, like taking the time not to try and carry that negative throughout the whole polynomial while you're actually doing the subtraction. Just write it out so you have individual terms and then combine the individual terms. So what we're going to do next now is multiplying polynomials. And the main thing that we're going to do with polynomials multiplication is we're going to use the distributive property of multiplication over addition. Okay? So monomials, we just multiply. Okay? You don't have to have like terms. You can multiply any two things together, and all your rules for exponents and coefficients and all that kind of stuff for signs, they all apply. And so when we multiply these two monomials together, we get 15x to the 5th. So with everything else, we're going to use this distributive property. And so let's say we have something like 3x times 2x plus 1. What you do is you take that 3x and you multiply it by each of these terms, the 2x, and then you multiply it by 1. So we get 3x times 2x plus 3x. Now, of course, you don't have to write it in this kind of excruciating detail. You know that 3x times 2x is 6x squared. So when you simplify it out, you get these two terms. So this is straight distributive property. The distributive property works both ways. So if you have something that's on the right side, you get the same kind of deal where you say, all right, I'm going to take this 2x, and then I'm going to multiply it by the 3x, and then I'm going to multiply it by the negative 1. And so when I simplify it, I get that. Okay, so now if we take two binomials and put it together, many of you probably know the acronym FOIL, and I'll talk specifically about FOIL on the next slide. But what we're really doing here is we're multiplying, we're using the distributive property twice here. First, we're taking that 3x and multiplying it by the 2x plus 1, and then we're going to multiply the negative 1 times the 2x plus 1. And when we expand all that, we get 6x squared plus 3x minus 2x minus 1, and then we combine those middle terms, and we get our polynomial in standard form simplified. Okay, so let's talk about FOIL. That stands for first, outside, inside, last. Okay, and so it's a way to keep organized when we take, and I'll take the same polynomial, that we're going to take the first ones, multiply that, and so we get 6x squared. And then the O stands for outside, so I'm going to use the outside, 3x times 1 to get 3x. And then I'm going to use the inside, negative 2x, and then use the last two terms, and I get minus 1. And so when I simplify it, I get the same polynomial. So you can remember the acronym. I rarely personally use the acronym. I just remember that everything has to be multiplied by everything else. And so you want to systematically go through it to make sure you get every term. And so you can, well, we can try a few first. Why don't you try multiplying these and then see what we get. just a little check to see how we're doing. So the first one is just a distributive property. Second one, you're going to use FOIL. Okay, so let's just go through these. The first one is going to be negative 6x minus 15x squared. And that's not in standard form, so we're going to rearrange the order and make that negative 15x squared minus 6x. The next one, anybody get an answer there? Yes?
2x squared plus 7x minus 15.
Good. Okay, so let's generalize FOIL then. You know, the first outside-inside last only works for binomials, but we can multiply trinomials in much the same way. And if you recall the way I used, arrows, you can do the same kind of thing when you have more than just two binomials. So what I'm going to do is just start. The x has to multiply everything, and then 2 has to multiply everything in the second polynomial. So we get x cubed, and then the second one, we get x times 3x makes 3x squared. Third one is x times 4 makes 4x. And since I've done every term, then I'm going to start with the 2. So I get 2 times x squared, 2 times 3x, 2 times 4 is 8, and now it's a matter of combining like terms. And I get that. Okay, so the process that you use for FOIL works for any number of polynomials that you have. You just make sure you start from the beginning and go all the way through for all the terms in the in both polynomials. Okay, so here's one that's a little bit longer even, trinomial. So we take x times x squared is x to the 4th. X squared times 4x is 4x cubed, and then x squared minus 1 is minus x squared. Then the second term, same thing. By all three, you get negative 2x cubed minus 8x squared, and then negative 2x times negative 1 is going to be 2x. And then you do the last one, x squared, 4x minus 1. Now on something like this, since I don't write in color when I'm working on a pad of paper, of course, I start canceling out. So I look for my highest term to put that one first, x to the 4th, and then I say, okay, do I have an x to the 3rd? I do, and in fact I have 2 of them. So I'm going to add those 2 together, and similarly do that with the rest. So the 8x squared, 6x minus 1. And you can see I just kind of crossed them out to make sure that when I'm done, I don't have any remaining terms that I've left over. So 2 things about this. If you want to use lines like this when you're working out, that's a good way to not avoid. That's a good way to avoid missing any particular term. So you can always make your little rainbows like this, and then of course canceling out. I'm not a fan of canceling division like this, but I think when you're adding a bunch of different terms, that it's pretty helpful in making sure that you're not overlooking anything, because it's hard to go back and check without actually redoing the problem. Okay, so you try this one now. And I'm probably going to pick on somebody again, mercilessly, like always. Let's see. Lou, when you're done, I'd like you to do this one, okay? So you can seek help from your neighbors if you get stuck. And so Lou, what you can do is just turn around and write it on the chalkboard behind you. Your answer, okay? Okay, drum roll, please. Here comes the answer. Okay, everybody get that? Doing okay with it? Everybody get it? Great job. Okay, so there I make my little diagram. Got the same answer, so we must be right. All right. Now we can do this for any, we can use that kind of format to multiply any two polynomials together. There are some special forms that I think are worth recognizing, because what we're going to do after we do this multiplication thing is we're going to start factoring, and we're going to take things apart. And so there's a few forms that really come out with some type of symmetrical or patterned look that once we know them from the multiplication side, from the factoring side, they'll come out pretty obvious. So when we have two binomials, and one is the sum of the two terms and the other one is the difference, what we get is a squared minus b squared. Okay, so in fact this one is very, very common. So when you see the difference between two squares, they're going to factor into the product of the sum and the differences. So if you were to do this out, by FOIL, you can see what happens is those interior terms, that a times negative b and then the b times a, will cancel each other out, and you just get the squares on the outside, and that last term is negative. Now when you actually square any sum of two terms, you get this a squared plus 2ab plus b squared look. So you have the coefficients of the first and the second term, you multiply those together, and then you multiply it by 2, and you get that middle term. So if you were to do this out, of course you would get a times b and b times a, and that's where the 2 times the ab comes in, is that you get it 2 times. You get it first from the outside, and then you get it from the inside when you're foiling this. And of course when you take the difference now, we get the same sort of thing, except that we have minus 2ab, and it's plus b squared at the end. Now it stays positive because you get minus b times minus b when it's spread apart and you do the FOIL thing. So you get the a times minus b and the minus b times a twice, so that's what leads to the negative 2ab. But you have negative b times negative b, which will be positive. So you always have this, this pattern at the end. Now, if you recognize or if you get comfortable with these patterns, it makes certain multiplications go very, very quickly. So in the simplest case, if we just have x plus 3, x minus 3, that'll be, x squared minus 9. But if we have coefficients and we take the sum and the difference, it still works. Just remember that you have to square the coefficient as well. So this comes out to be 4x squared minus 9. Now generally we're dealing with polynomials with one variable, but we will also see a few with more than one variable. So if we have 2x plus 3y, all the same rules still apply. This is going to be then 4x squared minus 9y squared. You see how the first term is squared, the last term is squared, and then you take the difference. Okay, so let's construct a few examples with the squared. So if we have x plus 3 squared, that's going to be x squared plus 6x plus 9. So what that is that we have a coefficient in front of the x of 1, and the coefficient on the second one is a 3. So we have 2 times 1 times 3 is how you get that middle term. And then, of course, the last term is just the square of 3. And if we build it up like we did before, we get 4x squared plus 12x plus 9. So the 2x squared becomes 4x. But if we look at what happens here, is that this is going to be 2x times 3 times 2. So it's going to be the product of each of the terms here, 2x times 3, and then multiply by 2, and that's what will be that middle term. And of course, just the square of the last term is the constant term at the end. And if we get into the realm of two variables, it works exactly the same. The y comes all the way through, including that middle term, and we get 12xy plus 9y squared. So it's the same sort of deal. You take the 2x multiplied by 3y, gives you 6xy, and then multiply that by 2, and you get 12xy. And similar examples when we take the square of a difference between two numbers. The coefficients stay the same, except the middle coefficient now is negative to reflect the fact that it's x minus 3 or 2x minus 3 or 2x minus 3y. And so we get that. Okay, so more for you to try here. There's 3 or 4 of them. Now I know I just barely give you enough time to do these, so I'm going to just give you a minute or so to start on them to see how fast you can do. While you're doing this, I'll tell you about my mean old algebra teacher when I was a freshman in high school, Ben Kingsley. He would always accuse us all of being incredibly wealthy students, which we weren't. But his justification was the fact that we were all wearing wristwatches, and he never had one when he was a kid, so we were all rich. So you can tell this was not a pleasant guy. So he started off with a list of these things, of 20 of them, and the first time we had 5 minutes to do it, the second day we had 4 minutes, and then he kept on clamping down on us until we can do 20 of them in 1 minute, and then they did it the other way around where we had to then factor first 20 in 5 minutes, and all the way down to factoring 20 of them in 1 minute. So I won't subject you to any speed tests like that, but none of us especially liked it. All right, so first one, x squared minus 4. That's the sum and the difference between two numbers. Here's the sum and the difference again, so we take the 4x squared minus 25. Here's x plus 5 squared, so we get x squared plus 10x plus 25. And the 4x minus 3 squared is 16x minus 24x plus 9. Okay, so I have a couple applications. And I know we're in the very last minute of the class, but basically we can do things like find volumes that involve expressions, polynomial expressions. And so volume is just going to be length times width times height. And so we can multiply all these 3 things together. And whenever you're doing this, just multiply 2 of the factors together first. And I think the second 2 work out. Then you multiply by the first one, and we get our result. And then I will start with this one, but I would like you to at least think about before Wednesday, how do you calculate the green area on this thing? So when you have something that's an area with a hole in it, how do you calculate its area? Okay, so we'll start with that on Wednesday. And so that's it for today.